geometry of the loss surface. Okay, so basically the loss surfaces are flat, maybe flat regions, or they may have local optimum. The differential curvature, so because we were talking about gradient descent, gradient directions are only locally optimal, so which they change over steps of finite length. So a direction which is changing, in which the gradient changes very very quickly, that shows that the surface is of high curvature. Okay, so the differential curvature is also important to be studied when we are looking at the loss surface geometry. Then we may also encounter some of non-differentiable loss functions, so which will be very challenging in order to find out the gradients. And in this case, the gradients may not give you any information in the regions with non-differentiable, like these may be the regions with having cliffs or valleys, that is the sudden drop. Okay, so we will see this one by one now. So you take let us look at the geometry starting with the one dimension. So if we look at this function, this is a one dimensional function, x minus 1 the whole square times x minus 3 the whole square minus 1. So if you apply the derivative test, the necessary and sufficient condition, and take the first derivative, equate it to 0, you get the solutions to be 1, 1.634 and 3.366. From the second derivative, you will be able to get the second derivative of the first and this third root. They are positive. Okay, and whereas the second derivative at this point is negative. And when you take the function's value at these points, you see that the function has maximum value at 1.634. So in this case, it was easy to solve for both the potential minimas by using the conditions, and then plug in the values to determine what is the global minimum. But what happens when we try to use the gradient descent? Okay, so let us see, let us think that if you start here, so in the previous example only, uh, if we start the gradient descent from any point which is less than 1.634, we will arrive at a local minimum if we always choose the wrong starting point in the multiple runs. And there would be no way of knowing that a better minimum exists. This problem becomes even more severe when there are multiple dimensions. So this is just one dimension, and the number of local minima are more. So another example here, which demonstrates the presence of flat regions, is this example. So this is an objective function which has a flat region. So in a while, I'll show you the graph of it. And you see that in this interval, minus 1 to 1, the gradient is nearly 0. So if you look at the graph, so it has a flat region in this range, okay, between a local minimum and a local maximum. Okay, so this is the flat region. So this type of situation is very common and is possible even if objective functions were where there are no local optima. Okay, so this function uh, is that which is demonstrating the flat region. So why are flat regions problematic? Because the speed of the descent, the speed of the descent, it depends on the magnitude of the gradient if the learning rate is fixed. So in such situations, the optimization procedure will take a long time to cross this flat region of the space. And this will make the entire process very, very slow. Okay. So for these kind of issues, something called as momentum methods are applied, which uh, which makes the descent little faster. So the basic idea with the momentum is that if it can be analogous to something like rolling a marble down a hill, so which can gather its own speed as it rolls down, and uh, you can often navigate, it will be able to navigate the uh, local potholes and the flat regions better because of that natural speed or the momentum that it has. Next, we have the differential curvature. So, in the multi-dimensional settings, the gradient component may have very different magnitudes, which causes problems for the gradient descent methods. For example, the neural networks, they have large differences in the magnitudes of the partial derivatives with respect to the parameters of different layers. So this entire process, this process of having the large differences in the magnitude of the partial derivatives is giving rise to what is called vanishing and the exploding gradient problem. So let us look at this with the help of simple convex quadratic objective functions. So we have these two objective functions here, x square plus y square, which is a nice symmetric curvature circular ball, and the other function is x square plus 4y square, which is an elliptical ball with higher curvature in the y direction. Okay, so if you look at its graph, it is like this. So in this figure, you see the contour plots of both the loss functions, uh, in which the lines, these lines are basically uh, the points in the xy plane where the loss function is having the same value. Okay, and the direction of the steepest descent is always perpendicular to this line, as we saw when we were seeing the line search. So the first loss function uh, um, is x square plus y square. So this is having nice circular circles. So and the second one is having this elliptical ball. Okay, so now this loss function is more sensitive to changes in the value of y as compared to the changes in the value of x. Okay, which will also depend on the position of the data point. So if you look at the second order derivatives of the loss function with respect to x and y, they are different in both the scenarios. For this, the high second order derivative I mean, is is very different from this. Why? Because the second order derivative for y here is having high curvature. Okay, so this is important from the perspective of the gradient descent, because it tells us that some directions have more consistent gradients that do not change rapidly. Okay, so in this case also you can see the gradient points directly uh, at the optimum solution, and you can reach the optimum in a single step as long as you take the correct step size. Okay, but this is not the case here. The gradients are more significant in the y direction as compared to the x direction. So the gradient never points to the optimum solution directly, unlike this loss function. As a result, many course corrections are required. Okay, and that is this zigzagging happens, and because the y direction gradient is more significant, the steps along this direction are also large, but subsequent steps will undo this effect of the previous steps, whereas the progress along the x direction is consistently.
Hello. ma'am, you are not audible. Hello.
Am I audible? Hello? Not audible.
Yes, ma'am. You are not audible before, but now you're audible.
Let me check. Since how long was I not audible?
Just 1 minute, ma'am.
Okay, so am I audible now
Yes, ma'am.
properly?
Yes, yes.
Okay. Okay, so we were looking at the differential curvature. So here you can see in this figure in which the gradients are more significant in the y direction as compared to the x direction. The gradient never points to the optimal solution in this case, as a result of which many course corrections are needed over the descent. And another observation is that steps along the y direction are large, but subsequent steps undo the effect of the previous steps. Okay. On the other hand, the progress along the x direction is consistent in this loss surface, but it is less. So, in other words, the long term progress along each direction is very limited. Therefore, it is possible to get into situations where very little progress is made even after training for a long time. Okay. This example was a very simple quadratic convex function which represents a very straightforward scenario as compared to the real world settings. Okay, so this was for the understandable purpose that why the loss surface geometry is important. Okay, so in fact, with very few exceptions, the path of the steepest descent in most loss function is only an instantaneous direction of best movement, and it is not the correct direction of descent in the longer term. So, in other words, the small steps with course corrections are always needed. Okay? The only way to reach the optimum with steepest descent updates is by using an extremely large number of tiny updates and course corrections, which is obviously very inefficient. At first glance, this might seem almost everywhere, but it turns out that there are numerous solutions. I mean, you of varying complexity to address these issues. That is, there are many variants of this gradient descent to accommodate these facts. Okay. Now let us look at some more loss surface topologies with high curvatures. So two examples of high curvature surfaces are cliffs and valleys. So in case of a cliff, there is a gently sloping surface that rapidly changes into a cliff. Okay. Uh, However, if only the first order partial derivative with respect to x is computed. So if you look at this cliff, so if you compute the first order partial derivative with respect to variable x, you will see a gentle slope. As a result, a modest learning rate, it might cause very slow progress in this gently sloping regions. Whereas the same learning rate can suddenly cause overshooting to a point far from the optimal solution in steep regions. So this problem is caused by the nature of the curvature. That is changing gradient, where the first order gradient does not contain the information needed to control the size of the update. Okay. So there are several computational solutions directly or indirectly making use of this the second order derivative, which contains more information about the lost surface to account for the curvature. Cliffs clearly are not desirable because they manifest a certain level of instability in the loss function. So this implies that a small change in some of the weights can suddenly change the local topology so drastically that continuous optimization algorithms like the gradient descent have a hard time. Okay. Uh, the specific effect of curvature is particularly evident when we encounter the loss functions in the shape of valleys also. So this is equally a dangerous topography for a gradient descent method, particularly if the bottom of the valley has a steep and rapidly changing surface, which creates a narrow valley as seen here. So in narrow valleys, the gradient descent method will bounce rigorously along the steep sides of the valley without making much progress in the gently sloping direction, where the greatest long-term gains are present. So many computational methods magnify the components of the gradient along consistent directions of movement to discourage this back and forth bouncing. In some cases, the steepest descent directions are modified using such ad hoc methods, whereas in the others, the curvature is explicitly used with the help of the second order derivatives. So the choice of the loss function is critical in defining the outputs from the neural network in a way that is sensitive to the problem at hand also. So for example, the least squares regression, okay, with numeric requires
Hello. Ma'am, your voice is like
am I still not audible? Am I audible? I'm not audible. It's not properly. Okay. So maybe
ma'am, your
what I
voice is
can,
lagging sometimes.
sometimes it's lagging. Okay. But my connection appears to be proper. So what I can do is I can rejoin. Okay. I will just exit for a minute and rejoin to fix this lagging and the audible issue. Okay. So I'm rejoining. audible?
Yes, ma'am.
Am I audible now?
Yes, ma'am.
Okay. So do let me know if there is any issue this time also. So we were looking at the choice of loss function, and we saw that it depends on the problem at hand. So this was the mean squared error, which is basically used to predict the numeric outputs. Then we also have probabilistic predictions with two different types of loss functions: binary cross entropy, which can be either in a binary classification or a categorical target. Okay, so the binary, for the binary target, you have two classes in which you predict the class label for the given sample. In that case, you use the binary cross entropy loss, which is given by minus of y log y cap plus 1 minus y log 1 minus y cap. So if your label is 1, the loss will be negative log of y cap, which encourages y cap to be belong to class 1. And if your label is 0, the loss will be such that it will encourage the predicted label to be 0. Okay, so this is a small example, numeric example with different values of it. So the loss will be low when the prediction is confident and correct. The loss will be high when the prediction is confident but wrong. So this is basically the penalizing confidence algorithm, the principle. So these are the figures, the diagrams for the binary cross entropy loss and the mean squared error. Both are convex in nature. So binary cross entropy is basically convex in itself. Okay, but it becomes, when it is used in the neural network setup, the the loss function of the neural network becomes non-convex. Okay, whereas if you use the binary cross entropy loss in the logistic regression setup, the loss function is convex. Okay, so the binary cross entropy loss is both convex and non-convex depending on the setup in which it is used. Mean squared error is a, you can see the graph here, which is a convex. And here the here you can see the 3D plot of both the binary cross entropy and the mean squared error. So the key point here is to remember is that the nature of the output nodes, the activation function and the loss function, they depend on the application at hand. Okay, all these together they make the loss function or the objective function of the neural network convex or non-convex. So even though the perceptron is often presented as the quintessential representation of single layer networks, it is only a single representation out of a very large universe of possibilities. So in practice, one rarely uses the perceptron criteria as the loss function. For discrete valued output, it is common to use softmax activation with cross entropy loss. For the real valued output, it is common to use the linear activation with squared loss. So generally, cross entropy loss is easier to optimize than the squared loss. Okay. So here you can see the visualization for the two labels. So for the binary classification problem, so for label y is equal to 0, you can see here the loss is minimized when your wx plus b is very, very less. That is, the predicted probability approaches 0 and the surface is smooth but steep near the decision boundaries. For the label y is equal to 1, loss is minimized when your wx plus b is very, very large. That is, the predicted probability approach is 1, and the surface is steep near the boundaries and curved. So for y is equal to 0, the minimum lies where the predicted probability is equivalent to 0, and for y is equal to 1, the minimum lies where the predicted probability is equivalent to 1. So neural network optimization is a multivariable optimization problem. These variables correspond to the weights of the connections in various layers. The multivariable optimization problems, they often face stability challenges because we must perform the steps along each direction in the right proportion. So this turns out to be very hard in the neural network domain, and the effect of the gradient descent step might be somewhat unpredictable. So one issue is that a gradient only provides a rate of change over an infinitesimal horizon in each direction, whereas an actual step has a finite length. So one needs to choose the steps of reasonable size in order to make any real progress in the optimization. The problem is that the gradients do change over a step of finite length, and in some cases they change drastically, as we have seen. The complex optimization surfaces presented by the neural network optimization are particularly very difficult in this respect, and the problem is further exaggerated with poorly chosen settings such as the initialization point or the normalization of the input features. So as a result, the very easily computable steepest descent direction also is often not the best direction to use for retaining the ability to use large steps. So small step sizes lead to slow progress, whereas the optimization surface might change in unpredictable ways with the use of large step sizes. All these issues make the neural network optimization more difficult than it would seem at the first instance. However, many of these problems can be avoided by carefully tailoring the gradient descent steps to be more robust to the nature of the loss surface. Okay. So this was about the loss surface geometry. If there are any questions, I am happy to take up on this. And if not, then I can start with the next session, that is on the activation functions. Okay, is my screen visible?
Yes, ma'am.
Okay. So are there any questions on the... Am I audible properly?
Yes, ma'am.
Yes, ma'am, you are audible.
Okay, so now we start with activation functions and their role in optimizing. So as we have already seen the challenges associated with the optimization of neural network and the loss surface geometry in the previous section, now we will dig more deep down in the entire optimization process with the very important part of the entire neural network setting, that is the activation function. So what is an activation function? Before that, we will see some basic mathematical definitions to motivate the definition of activation function. So first is the function. So basically what a function is a process that takes an input, processes it, and produces an output. Okay. So this representation, you can see this process that is which shows function as a machine. Okay. Takes the input x, uh, gives us the output y, and this is the rule that governs it. So it's like feeding raw ingredients into a machine and getting a dish. The second way of representing it is a mapping view. So here you see a function maps elements from one set to another set with a domain containing input set and a range containing the output values. And this curve is the function which associates each x with a y. So now the different rules of a function are: it is defined for every input. That is, every value in the domain must map to an output. And exactly one output is one input should not map to multiple outputs. Okay. So for example, here you can see the set with inputs that is mapped to output. So this satisfies both the rules. Each input has only one output and is a valid function. Whereas this function here, the input set with is shown with the mapping to multiple outputs. So this is violating the second rule, which says that it has only one relation for each input value. So here you can see in the graph also this vertical line, it touches the curve at more than one point. So this is violating the definition of the function, and this is not a function at all. Okay. These are some parent functions: constant, linear, absolute value, greatest integer, which is a stepwise graph, then parabola, cubic, square root, exponential, and so on. So these are some parent functions which are useful in the understanding of the foundation of the activation functions. Okay. And these are your periodic functions: sine, cos, and tan functions. Now next is the continuity. Okay. This is again essential, uh, especially in optimization and the gradient based learning. So continuity function is said to be continuous at a point if its limit at f of x as x tends to a is equal to the function's value at that point. That means the function doesn't have any jump or break. Graph is continuous and has no jumps. As you can see here, this is a continuous function and this is a piecewise continuous function. Okay. uh, Continuity again is a foundation for what we are going to see next. Then comes the differentiability. So differentiable function is a function if the derivative exists, that is this limit as h tends to 0 exists, that is the slope of the function is well defined and it is finite. So for example, this is a smooth graph and there are no sharp corners or cusps or verticals. As compared to this, it has a sharp corner here. So this is a differentiable function at all the points and this is not differentiable at this point only. So these are again, the differential functions are critical in the gradient based methods. And these methods, because they rely on computing smooth slopes to minimize the loss in the deep neural networks. Okay. So it is essential for the optimization algorithms. Next is the monotonic functions. Again, an important idea. Monotonic functions are of two types: monotonically increasing. That means the function never decreases as x increases. So if you are increasing x, a function is also increasing. Monotonically decreasing, function never increases as your x increases. So monotonic function, they basically preserve the order during transformations, which is important for ranking, normalization, nonlinear scaling, and interpretable models. I hope I'm audible.
Yes,
Yes,
ma'am.
ma'am. Yes.
Okay. So these are some of the examples. So this is monotonically increasing, this is monotonically decreasing, and this is alternating between increasing and decreasing. So monotonic functions, they make the data transformations predictable and stable. Okay. So understanding monotonicity is very important in optimization, probability and statistics, and deep learning in order to understand the activation functions. So here we compare the linear and non-linear functions, how they differ in its behavior and application. So linear functions, here the rate of change, the slope is constant, and output changes proportionally with the input, but it cannot capture the complex patterns. Okay. Whereas the non-linear function, the graph includes curves and bends and direction changes. The slope is not constant here, it varies with the input. It can capture the non-linear function, they are capable of capturing complex and real world relationships. These are essential in the deep learning and AI because it allows the neural network to learn the non-trivial patterns. So these are some of the examples of linear and non-linear. So non-linear functions are powerful, flexible for the real world modeling. In non-linear risks the electrical signal.
Hello.
Uh,
Ma'am, you are not audible.
am I not audible?
You are not
Am
audible
I not
from past 2 minutes.
okay? I don't know what is happening in the network. I am connected very well with the network. Yeah.
Now
Am I
also
audible
is fine.
now? Now it is
Yes,
fine.
ma'am. Now it's fine.
Okay.
Yes.
Okay. So, like the biological neuron, the artificial neuron also functions. It takes inputs uh, uh, like signals coming in from the other neurons, these X0, X1, X2, etc. Then there are weights which indicate the strength of each input, like the synapse strength in the biological neuron. Then you have the bias, which is a constant added to shift the result. So this helps with flexibility. And then we compute the weighted sum and apply the activation function, that is applying a non-linear transformation like decision making in the biological neuron, which gives us the output, which is passed to the next layer, just like how the axon transmits the signal. Okay. So with this background, now we come to what is an activation function. So an activation function is a mathematical function applied to the output of a neuron to introduce nonlinearity, help the network learn complex patterns, and control what signal the neuron passes forward. Okay. So basically the activation function is adding a nonlinearity. Without activation, a neural network becomes just like a linear model, no matter how many layers you keep on adding. So activation function is allowing the network to approximate any nonlinear function, which is the case in the real world scenario. It is converting the weighted sum to the output. Okay, so it passes it through a function f to get the output y. Activation function is further enabling the learning of complex patterns, okay, which helps the model non-trivial and learn the real world relationships. The choice of activation function further affects the gradient flow during the backpropagation, convergence speed, and the stability of the network. So we have various types of activation function. There are linear activation functions where the graph is a straight line, commonly used in the regression problems. But there is no non-linearity. It cannot capture the complex patterns. So that is why they are not used in the deep networks. Okay. Non-linear activation functions, they introduce the non-linearity, which enables the network learn complex relationships and model real world data. For example, you have the sigmoid function that we used in the last session in that small numerical example also, which outputs in the range 0 to 1. Further, we will see more about it. Step activation function, again it behaves in a binary output format, and historically it was used in early perceptrons. The limitation of this step activation function is that it is not differentiable, so the back propagation doesn't work and you cannot compute the gradients. So it is not suitable for the modern deep learning. So the activation functions that are used in the deep learning models are the nonlinear activation functions, which we will see more about. So before that, let us see if we did not have the activation functions at all. So as I already mentioned, that if without the activation function, a neural network behaves just like a linear regression model. It becomes just a series of linear transformations, and that is multiplying by weights and adding biases. Okay, so that is if you layer 1 O1, you get output to be O1, and then layer 2 is again a linear, layer 3, because the composition of linear function is again linear function only. So without activation function, the network cannot learn nonlinear patterns. It will fail on the real world problems like the image recognition, NLP understanding, and all that. And why this matters in the optimization? Because back propagation is the one that we use to train the weights, which aims to reduce the loss also. That is how the weight training happens. So but if the network is linear, the model capacity is also limited no matter how much you optimize. Okay, so we will see this this demonstration with the help of a simple example here. So here we have, I hope I'm audible.
Yes, ma'am. You're nicely audible.
Importance of non-linear activation functions. So if you consider an example of say 3 points, okay, so we have this A, which is -1 and 1, and its class is star. So A point is belonging to star class. You have B point 0, 1, which is belonging to plus class, and C point is having 1, 1, which is belonging to star class again. So you have two classes, star and plus class. You have 3 points which are not linearly separable in their original 2D space. Okay. So what happens is we consider this neural network architecture with the two input nodes. So we consider two input nodes, x1 and x2. Okay, and two hidden neurons. with this edge, let us give this +1. With this edge, let us give this -1. The edge going from here to here, 0, and from here to here, it is 0. Then you have the output. So then you have the output. So this is H1, this is H2. Okay. So when we consider this, what happens is we have the H1, we get it as some activation function times W11 x1 plus W12 x2. Okay. Let us take this output function to be ReLU activation function. W11 x1 plus W12 x2. So what is this ReLU activation function? Basically, this is the maximum. ReLU is maximum of x 0. Okay. So if you consider this, then what happens is your initially not linearly separable points are separated as linearly separable. How? So with this, you get H1 to be a ReLU of 1 times x1 plus 0 times x2, which is a ReLU of x1, and H2 similar on the similar lines, you get -1 times x1. So I'm just considering the weights that we have assumed, plus 1 times x2. So that is a ReLU of minus x1 plus x2. Okay. So point wise, if you see for the point A, that is -1 and 1, your H1 is given by ReLU of x1, which is -1. That is 0. And H2 is ReLU of -1 plus 1. That is ReLU of 2, which is 2. So the output is given by H1 plus H2, which is 0 plus 2 is 2. Similarly, for the point B, 0, 1, you have H1 to be 0, H2 to be 1, and the output is 1 on the similar lines. Okay. For the point C, which is 1, 1, your H1 is 1, H2 is 0, and the output is 1 plus 0 is equal to 1. Okay. So this is how now it is clearly you can separate it. You can separate it linearly. Okay. With these outputs, you can separate it linearly. So that is your not linearly separable. So if I have to draw the diagram, so A was in star class, B was in plus, and C was in star, which was not linearly separable, has been with the first layer transformation itself, which we computed these calculations. You have separated it linearly. So A star, B is plus, and C is star class. So this is a linear separation that has happened with the first layer of transformation itself. So let me draw it. So this is what the activation function does. So there are many choices, many alternative choices for the weights that can make the hidden representation linearly separable. So therefore, the learned weights, they may differ from what we have assumed here. So what we have done is the activation functions, they have enabled the nonlinear transformation of the data that become increasingly more powerful with the addition of layers. So a sequence of nonlinear activations imposes a specific type of structure on the learned model, so whose power increases with the depth of the sequence, that is the number of layers in the neural network. Okay, and this also is data driven. Okay. So this is how the real world data looks like. Okay, and we require this kind of non-linear boundary that is given with the help of the non-linear activation function, which is adding some kind of flexibility to the neurons by letting the neurons respond differently to different inputs rather than just producing a linearly scaled output. Okay, so these are essential for the deep learning task. So without the nonlinear activation functions, neural network would be no better than a linear model. Okay. Now, we have certain laws for the activation functions. These are the 5 essential properties. First is the nonlinearity. Uh, as we have already discussed, it enables modeling of complex real world data patterns by adding that uh, nonlinearity. Monotonicity, uh, that is, we have already seen that it should ideally always increase or always decrease. Why this is useful? Because it helps the gradients stay predictable and stable, which improves the training consistency. Next is continuity. It ensures the smooth learning and it avoids the abrupt changes in the neuron output. Then we have the differentiability. The activation function should be differentiable almost everywhere to allow a smooth optimization. Then finally, we have the computational efficiency, which saves the training time and computational resources. We also want, the function should to be zero centered. A function is zero centered if it is output. So here you can see the tan hyperbolic function. So this is zero centered. Why? Because its output is distributed around zero. That is, it produces both positive and negative values, roughly balanced around zero. So why this zero centered activation functions are important from the point of view of deep neural network optimization? Because in backpropagation, gradients are computed using the chain rule, as we saw in the previous section. So if activations are not centered around zero, the gradients tend to be all positive or all negative. So this can lead to inefficient weight updates, especially in the gradient descent. So for example, suppose the output of the layer is mostly positive and you are multiplying it with the upstream gradient. The updates will bias all the weights in the same direction, leading to a slow convergence. We also require faster convergence from the activation functions. The gradient updates, when activations are zero centered, the gradient updates are more balanced, and this leads to more efficient learning as the weights move in a direction that better align with the loss function. Finally, non-zero centered activations like those of sigmoid or ReLU, as you can see here, they can cause bias shift. That is, successive layers, they accumulate the non-zero mean outputs, leading to imbalance in the network. So this often requires the batch normalization to correct. Okay. So an ideal activation function should introduce the nonlinearity, be monotonic, continuous, and differentiable, be computationally cheap to use, and choosing the right activation function, it depends on your task, the architecture, and trade-offs between the speed and the performance. So choosing a right activation function depends on the network depth and the training behavior, and of course the problem at hand. So these this is an overview of some modern activation functions, that is the state of the art, used in commonly used in the deep learning architectures. So first is the ReLU, rectified linear unit. So you can see the ReLU here. We will see their individual graphs in the coming slides. So you have the ReLU, where which is popular in ReLU, leaky ReLU, and ELU. They are popular for hidden layers because they uh, as we will see in the next slides that uh, they they are efficient centered one,
Ma'am, you are not audible.
but again this also suffers from vanish grading problem. Then have uh, not audible. Am I not audible now also?
Now audible, ma'am.
I don't know. I think there is some network issue with the
From
institute.
previous 2 minutes, your voice is breaking.
Okay, now also is it breaking?
No, ma'am.
Okay, so what I was saying is these are some modern activation functions which are used in the deep learning, deep neural networks. And now we will look at all of them one by one. So first is the sigmoid activation function. It's mathematical formula one upon one plus e power minus x uh, one, which is ideal for expressing probabilities. Consistent gradient direction, it makes the optimization stable in shallow setups. The biggest disadvantage here is vanishing gradients. The gradients become too small, making it very hard for the deep networks to learn. It's not zero centered, it's having very slow convergence, because deep models like the VGG or the ResNet, they avoid a sigmoid in the hidden layers because of its slow convergence. um, Once I mean, it has a neuron saturation also. This is also one of the disadvantage, because once it is stuck, once the stuck in saturation, neurons don't activate only. So what both these problems are, we will see one by one mathematically: the vanishing gradient, exploding gradient, and the decaying neuron problem. Computationally it is costly. Sigmoid function is also computationally costly. So generally the sigmoid is used used in classification type of problems and on the final output layer. Okay, in the hidden layers of deep networks, it is generally avoided. And in multi-class problems, the softmax function is used instead of the sigmoid. Then we have the tan hyperbolic. So before seeing the tan hyperbolic, I would like to explain the vanishing gradient problem. Vanishing gradient. So suppose uh, we have uh, uh, have m plus 1 layers, including the layers. We are only using bronze in every. So these are the notes. I hope my voice is clear now.
Not completely clear. Can you just close it and then reopen?
My voice is still not clear.
Now
Clear, ma'am, but
it is
after
clear,
every
but
2 minutes it's
sometimes it's
lagging.
breaking.
My screen is visible properly.
Yeah, my
Yes, ma'am.
screen is properly visible.
Okay. So maybe what we can do is I will continue for 5 more minutes because we have an external speaker coming at 12:15. So I will cover whatever I can in the 5 minutes and then continue my talk in the post lunch. So hopefully by that time the issue will also be fixed. Was it audible?
Yes, ma'am.
Okay, so we have this m plus 1 layers, and they the weights are denoted by w1, w2, etc. Wm, and this x is the input, and we have some hidden layers hm minus 1, and this is hm. Okay, so back propagation update is like this. So if you have the loss function as L, so at every node, it is going to be some pi dash of H t plus 1 times W t plus 1 times the loss with respect to t plus 1. So here phi dash is the derivative of the activation function. Phi dash of ht is the derivative of the activation function in hidden layer T. Okay, and uh, and we will use the sigmoid activation function here. So let us have your f of h, that is the activation we are using is the sigmoid 1 upon 1 plus e power minus h. So your output basically is ranging from 0 to 1. Okay. Now derivative of this sigmoid function is f of h times 1 minus f of h. This you can evaluate mathematically and check that this is the case. So this is a quadratic function in f of h, okay, and it's maximized at f of h is equal to 0.5. So you use the rules that we discussed, the necessary and sufficient condition that we have discussed in the previous lecture. So your f of h at f of h is equal to 0.5. Your f dash of h becomes 0.5 times 1 minus 0.5, which is 0.25. Okay, so the maximum value of the sigmoid derivative is 0.25, okay, which occurs at f of h is equal to 0.5. That is h is equal to 0. So now when we see f dash of h is always less than equal to 0.25 for all h. So when now we track the gradient, okay, when we look at this chain rule again with this fact, what we see, del L upon del HT is equal to del L upon del HT plus 1 times del HT plus 1 upon del HT. Now what is this? We assume that okay, so we have already, yeah. So we assume that the weights, I mean the modulus of the weights are initialized from a standard normal distribution. So standard normal distribution basically is having the mean 0 and variance 1. So f dash of h of t is always going to be 0.25. So what this rule says is del L upon del h t is less than equal to 0.25 times del L upon del h t plus 1. Okay, so now you see that the magnitude of the loss function, the rate of change of loss function with respect to ht is very less than 0.25 times the rate of change of the loss with respect to ht plus 1. So when this happens over r layers, so this repeat over r layers, okay, r is a subset of m that we considered earlier. So what do we have? Del L upon del HT is less than equal to 0.25 to the power r times del L upon del HT plus 1. So you can see that the gradient is reduced to this term of its original size. Okay, so one can conclude that there is this vanishing gradient problem. So what happens is the earlier layers, they get almost no gradient, which implies the weights don't update, which implies the network stops learning from the earlier layers. This is the vanishing gradient problem, whereas the opposite is the exploding gradient problem. When it happens, when the gradients are that is when the derivatives is greater than 1 or large weights are used. So in this case, this inequality is reversed to del L upon del HT, very, very large than. So this in this case, the gradients blow up layer by layer.
Ma'am, voice is not audible.
Uh,
Voice is not coming, ma'am.
Post lunch session. Okay, so we have
Ma'am, your voice is not coming.
okay, so we will